Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions and equilibrium of a body. This exercise was a previous one in the brevet exams in 2007 second session, third exercise. The title of this exercise is Tension and Elongation of a Spring. Consider an elastic spring and a solid S of mass m. Take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of the Earth. Then part 1 of this exercise, characteristic of the spring. The adjacent figure shows, they mentioned this figure, then now we can use it. Within the elastic limit of the spring, the variations of the tension T as function of the elongation delta L of the spring. So notice that this curve shows the variation of the tension T expressed in newtons as function of the elongation delta L expressed in centimeters. And this is the curve, which is a straight line passing through the origin. Now number 1, referring to the graph, complete the table below. So let me draw the table. The table consists of 3 rows and they are given by the tension T expressed in newtons, the elongation delta L expressed in centimeters, and the ratio which is given by K is equal to T divided by delta L. So the unit of K, since T is in newtons and delta L is in centimeters, so the unit of K is expressed in newtons per centimeters. So this table, other than this column, consists of 3 columns. The given values are given by 2, 2 and 6 here. And let me complete the table using another color, which is, for example, blue. So we are completing the table graphically. So this is important. Now we will complete the first 2 rows by referring to the curve. Then after we have completed the first 2 rows, we can determine K by calculation. So now when the tension is given by 2 newtons, so this is 2 newtons, which corresponds to this point on the curve, which has a value of delta L is equal to 1 centimeters. So here notice that delta L is in centimeters, which is the same unit of the table. So here we have 1, and this is done graphically. Now when delta 2 is given by 2 centimeters, so it corresponds to this point on the curve, which has a value of 4 newtons. And when the tension is given by 60 newtons, it corresponds for this point on the curve, which has a value of delta L is equal to 3 centimeters. So graphically, we have completed the first 2 rows. Now by calculation, we'll complete the third row. So let's do the calculation here. So let's start by the first column or the first value. So K is given by T divided by delta L. When the value of T is given by 2, so for the first column, delta L is given by 1. Then the value of K is given by 2 expressed in newtons per centimeters. Why newtons per centimeters? Although the unit of K, we know, and the SI is given by Newton per meter, because here in the here T is expressed in newtons and delta L in centimeters, and the table, the unit of K must be newtons per centimeter. So here we have the value of 2. Now as for the second value, which is given by K is equal to T divided by delta L, which is given by 4 divided by 2, and we expect the same answer, which is given by 2 newtons per centimeter. So here the value of K is given by 2. Notice that I'm not including any unit for these numbers because the unit is already included in the first column. Finally, the last value of K is given by K is equal to T divided by delta L, which is 6 divided by 3, and given by 2 newtons per centimeter. So in this case, the value of K is also given by 2. So this is it for part 1. Now in number 2 they are telling me K represents a characteristic physical quantity of the spring. So part A, give the name of this characteristic. We know that the K represents the stiffness or the force constant of the spring, because simply it is the ratio between T and delta L. Then now we are in number 2. So what does it represent? Give the name of this characteristics. It is the stiffness of the spring, and between brackets this is known as the force constant. And now in part B, give its value in the SI. So we already know the value of K to be 2 newtons per centimeter, but here they are telling me to give the value of K in the SI, so we need to convert K to the SI, knowing that the Newton per centimeter is not the SI unit of the stiffness. In order to convert from Newton per centimeter to the SI, which is given by Newton per meter, we simply multiply by 100. Then 2 multiplied by 100 is given by 200 newtons per meter. Then the value of K in the SI is given by 200 newtons per meter. So here let me write that the stiffness of the spring that we are using is given by 200 newtons per meter. So what does this mean? In order to elongate the given spring by 1 meter, we need to exert a force worth of 200 newtons. And now in part C, give the name of the law that gives the relation between Tk and delta L, and this is for sure is known by Hooke's law. Now in part 2, equilibrium of solid S, we suspend the solid S from the free end of the spring balance as at rest. So for sure they are talking about this document. So here this is important. S is at rest, which means that S is not moving. Or in other words, it is at equilibrium. Now number 1, give the name of the two forces acting on S. So because this solid has a mass which is denoted by capital M, then it will be directly subjected to the weight which acts on the solid S on the point on the center of gravity vertically downward. So this is the first force. And the second force here, because we have spring, whenever we have spring or string, it will be directly subjected to the tension T, and it has a point of application which is the point of contact between the solid S and the spring. So this is the tension T acting on the solid S along the string vertically upward. So the forces are given by the weight W vector and the tension T vector. Now in number 2, write down the vector relation between these two forces. So they are asking me about the vectorial relation, or other words, the condition of equilibrium. How do you apply this condition? Always we start by writing the title, which is given by at equilibrium. And how do you apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by the weight and the tension. Then weight vector plus tension vector, and on the other side of this equation we'll write the 0, and we don't forget the vector because this is a vector equation. Each quantity must include a vector. Now moving T to the right hand side, we have that the W vector is equal to minus T vector. So let's give the physical significance of each equation. The first equation tells us that the effect of both forces acting on the solid S cancel each other to give us the 0 vector, which is the equilibrium. Whereas the second equation means that both forces have the same line of action, opposite direction for the minus sign, and same magnitude. Let me make some space here. Now number 3, deduce the relation between T and M, and by deduce it means we need to use the part just previously before, in which we have determined the vector relation. So let's say that the W vector is equal to minus T vector. So we need to deduce a relation between T and M. So by relation, so probably they mean an equality between T and M. So here T and M represent the magnitude. So T represents the magnitude of the tension T, and M is the mass of the solid S. So here let's say in magnitude. So what will happen here that we will drop down the vectors and get rid of the minus sign, so W is equal to T. But notice that the required relation is between T and M and not between W and M, so let's replace W by M times G. But we know that W is given by M multiplied by G. Then in this case, we know that T is equal to M multiplied by G. Then the required relation is given by that T is equal to M multiplied by G. So this is the required relation. So what do we benefit from this relation? We know that in physics, any equality consisting of three quantities, we can construct a triangle for this formula. So here, because we have multiplied, and T will be at the top, M and G at the bottom. So for example, knowing the value of T and G, putting our hand over M, then M, for example, will be given by T divided by G. And now let's continue part 3 of this exercise, the final part. Elastic limit of the spring. The maximum elongation of the spring within its elastic limit is given by 7 centimeters. So what does 7 centimeters represent? It represents the maximum elongation. Then let me write here that delta L max is given by 7 centimeters. If we suspend a mass of 1.7 kilograms, the spring loses its elasticity. So here we have the mass to be measured is given by 1.7 kilograms. So they are telling me that the answer is that the spring will lose its elasticity. Justify referring to the curve. So we need to justify this answer by referring to the curve. So here what's happening is that we have this spring. So knowing that this spring can be elongated by a maximum elongation given by 7 centimeters. So now if we suspend this mass M to the free end of the spring balance, the spring will elongate. Now we need to justify why the spring will lose its elasticity, knowing that the maximum elongation is given by 7 centimeters and the mass to be measured is given by 1.7 kilograms. In order to justify why the spring loses its elasticity, we need to determine the maximum mass that the spring can measure, and this can be calculated from delta L max. Okay, so how we will calculate the maximum mass from delta L max? So by referring to the curve. Notice that here, knowing delta L and referring to the curve, one calculate the maximum tension that the spring can undergoes. So then using this relation, knowing T and knowing G, we can determine the value of M. So first, let's say graphically, why we are referring to the graph here, because they are telling me, they gave me the following hint, justify referring to the graph. And here I repeat that, or let me say that they give half a mark for this statement. So let's say for delta L max is equal to 7 centimeters, we have that the maximum tension is given by, so delta L max has the following value, which is given by 7 centimeters. It corresponds to this point on the curve, which has a value of T is equal to 14 newtons. And notice that the curve stops here. So T max is equal to 14 newtons. Now we have the value of T max is equal to 14 newtons. So what does this maximum tension represent? So this is the maximum tension that the spring can undergoes without losing its elasticity. Now knowing T max and knowing the value of G, which is given by 10 newtons per kilogram, we can determine the maximum mass. So let me say that T is equal to M multiplied by G. We are interested in determining the maximum mass that the spring can measure. So constructing the triangle of this formula, here because we have multiplied, then T will be at the top, M and G at the bottom. We are interested in determining the value of M, which is given by the maximum mass, which is equal to the maximum tension divided by G, which is given by 14 divided by 10. So plugging this fraction on the calculator, it will give me 1.4. Since both T and G are expressed in the SI, so the value of M max will be in the SI, which is kilograms. Then M max is given by 1.4 kilograms, What does this mass represent? It is the maximum mass that can be attached to the spring without losing its elasticity. Now we can answer this question. So notice that the mass to be suspended to the free end of the spring balance is given by 1.7 kilograms, whereas the maximum mass that the spring can handle or measure is given by 1.4 kilograms. So notice that because 1.7 kilograms is greater than 1.4 kilograms, for this reason the spring loses its elasticity. Then let me make some space here, and we will continue this part above, yet we didn't finish this part. So let's say since the mass to be measured is greater than the maximum mass, and between brackets let's say that 1.7 kilograms, so this is the mass to be measured, is greater than the maximum mass is given by 1.4 kilograms. We know that in this case we have, so either the spring balance will break out or it will lose its elasticity. Since here they are telling me it will lose its elasticity, then let's say then the spring, so here let me say also spring or spring balance is the same, then the spring loses its elasticity. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.